Hi, grade nines. Let's begin our third unit. This is the physics unit, and we'll be focusing on electricity. So our first lesson, lesson 1, is from section 10.1 in the textbook, okay? And it's entitled Exploring Static Electric Charge. And there are a series of homework questions there for you to practice with, and it's very important that you attempt those, especially in this unit, because I think it's a little more calculation based, maybe in some cases, not always as intuitive as the biology unit. And so it's very important that you keep up with the homework, in particular for the electricity unit, so you're getting all that practice in and it's deepening your understanding. Okay, so electricity, we all know what it is because we use it all, but what's our definition of it? Okay, it's a form of energy that results from the interaction of charged particles like electrons and protons. Okay, now we depend on electricity. There is nothing that we can get done without electricity. Okay, but generally speaking, the production of electricity, it has a huge environmental cost because it generates a lot of greenhouse gases. Now, here in Southern Ontario, a lot of our electricity is generated at Niagara Falls. It's hydroelectric, and so that's relatively clean, but we're actually in the minority. There are a lot of places, even in Ontario, that are still generating electricity with coal, okay? And that's not good because that generates a lot of greenhouse gases, okay? So we have to start figuring out different ways of harnessing electricity or other sources of electricity if we want to continue our way of life. And just as an aside, I listened to a great podcast. It's called Science Versus, and hopefully I'll remember to post that link here. There is a podcast about alternative sources of energy and whether we could power, well, the podcast is American, so it's whether we could power the United States on alternative renewable source of electricity. And spoiler alert, the answer is generally yes. The technology exists. The infrastructure doesn't exist quite yet to do that. We're sort of built for fossil fuels, but the technology exists in such a way that we could power nearly everything except for airplanes with renewable energy resources. So I will post that podcast link here with this. I'm going to try to remember to do it. Hopefully I'll make a note to myself and I'll do it when this video goes live. Okay, but what we have to do, and this is us as individuals, is we have to conserve electricity. If we know that there's an impact on the environment based on the amount of electricity we use, what we have to do is on our own say, well, I'm just not going to use as much electricity. I'm not going to waste it. Okay, I'm not going to waste energy because it has an impact. When all of us do it, when all of us are wasting electricity, there's an impact. Okay. Okay, we're going to take a look at two types of electricity. The first is called static, okay? And that's a type of electricity where the charge stays on the surface of an object. It's not moving. That's why we call it static, okay? The other type is current electricity. And that is electricity that flows through a pathway, some kind of a pathway. And we're going to learn more about that as time goes on, okay? But static electricity and current electricity, those are the two types we're going to learn about, okay? So static means stationary or not moving, okay? So static charge tends to refer to an electric charge that stays on the surface of an object rather than flows away. And there are three ways that we get static charge, okay? So there's three ways that we can cause that charge to stay on the surface of an object instead of moving. Charging by friction, charging by induction, and charging by contact. And we're going to dig into those three methods. Okay, and hopefully in digging into those three methods, we're going to answer the question of, well, where does this, you're talking about charge, but I don't know what that is. So hopefully we're going to answer that question as we go. Okay. We're bringing this back. Remember this from chemistry? I thought maybe you thought that we were done with this, but we are not. Because here's the thing about science, is that we separate it into chemistry, biology, physics, these three branches, but really they're a lot more connected than we often like to talk about this early in your education. I mean, because all the biological processes going on in my body, that's based on biochemistry, and electricity has to pass through physical matter, and physical matter is made of atoms, which is chemistry. And so there's this connection between chemistry and physics. And so there's a deep connection between all the three branches of science that we talk about. And so you can't escape it. And so the stuff we learned in chemistry, it to some degree is relevant here. Okay, now it's the basics. It's nothing too complicated. Okay, so hopefully we remember that atoms are made up of three particles, three subatomic particles. We have the positively charged proton, it's in the nucleus. We have the neutron, which is neutral, it's also in the nucleus. And then we have the electron. And the electron is that negatively charged particle, and it's orbiting the nucleus. Okay, and hopefully we remember that it's orbiting in those distinct shells. Okay, we fit 2 electrons on that inner shell, and then we can fit up to 8 on the next shell, and so on and so forth. And hopefully this diagram that's displayed here, hopefully you're looking at that going, oh yeah, I remember that. It's not a huge deal. Okay. Okay. Here's what the Bohr-Rutherford model explains. Particles that carry electrical charges can either be created or destroyed. Those electrons and those protons, they have an electric charge, they can't be created or destroyed. Yeah, that's true for now, but in a few years, maybe you'll put a star beside that and say except when. But for now, they can't be destroyed. It's as small as it gets. We cannot destroy protons or electrons. Okay. Any net charge on solid objects results from the transfer of electrons between this object and another object. Okay, so remember, protons, they're locked in the nucleus. They do not move. Okay, we are not going to get, under normal circumstances, an atom to gain or lose protons. What can move, what is free to move, or what are free to move, are the electrons, those negatively charged electrons. Remember, we gain and lose those all the time in chemistry because they're generally somewhat, to some degree, free to move. Now, some materials have electrons that are a little easier to move than other materials, okay? But generally speaking, electrons, free to move, okay? So, if you have a neutral object, okay, it has the same number of positive and negative charges, same amount of positive and negative. That's why it's neutral. The positives counteract the negatives. If you happen to have more electrons than protons, you're going to make the object negative. If you have the opposite, less electrons than protons, then the object will become positive. Okay? And this last point is just what I said. I forgot it was written here at the bottom. Different materials hold on to their electrons with different strengths. Okay? So some materials do not want to gain or lose electrons. Some materials, it's very easy for them to let electrons go. Some materials find it very easy to grab electrons from other materials and pull them close. So there is that difference. Okay? Simple atomic structure here. Okay, so there's obviously a nucleus in the center, and there's some electrons orbiting around. Okay, basic. We learned that in chemistry. That should be solid. We learned that in person. Remember when we could do lessons in person? 20 years ago, feels like. Okay, so in the center, that neutron, no charge. Proton, it's positive. Okay, and on the outside, ooh, look at that go. That's fancy distance learning right there. That is state-of-the-art technology. That's the electron, and it's negative. Okay. So if we look here, I know the colors are really, really similar, but the protons look like they're red, the neutrons are orange, and the electrons are obviously blue. We have 2 protons in this diagram, 2 protons, and we have 2 electrons. Okay. So that means that the image that we're looking at here is neutral. It has no net charge because the negatives and the positives cancel each other out. Okay. Whoa. What is that? See that fly in from the left of the screen to the right of the screen? That was an electron. Okay, so whatever happened here, and don't worry about the details. Oh, but there were 2 electrons. It's the first thing you should. No, don't worry about that. Just worry about, oh, I had 2 electrons. Okay, and then from the left side of the screen, or was it the right? Is it your right hand side? I don't know. I guess that's the right hand side. Went from right to left. Okay, an electron flew in. Okay, and that's an extra electron. So now we have 3 electrons and 2 protons. So 2 protons, 3 electrons. What charge will this have? Well, it will have a negative charge, okay? Because there's more electrons than protons now. Okay? Okay. What happened there? They left. They exited screen right. We lost 2 electrons. We lost 2 electrons. So now keep count. How many electrons do we have? We've got 1 electron. How many protons do we have? 2 protons. So what charge do we have? Well, we've got more protons than electrons now, so we should have a positive charge. Okay? Okay. Causes of electric charge. Most objects are electrically neutral because they contain equal numbers of positive charged protons and negatively charged electrons. We looked at that when we were doing chemistry, and what we found was, yes, it's possible to gain or lose, but even when we gain or lose electrons, we connect with another object that's either done the opposite, either gained or lost electrons, we become neutral. And so generally in our world, most things around us are neutral. We're not being electrocuted every time we touch something, and so it stands to reason that most things are neutral because they've got an equal a number of positive protons and negative electrons, okay? But when we take different materials and we rub them together, okay, we can build up a static charge. When you take 2 neutral objects, but they're made of different materials, so not my 2 hands because they're the same material, okay? 2 different materials, and we rub them together, electrons from the atoms in one material can transfer to the atoms in another material. And that process is called charging by friction, okay? And that's a process in which objects are made from different materials. They rub against each other, okay? And they produce a net static charge because electrons are moved from one of the objects to the other, okay? So when an object becomes charged by friction, one material has a stronger hold on electrons than the other material. That's why they have to be 2 different materials, okay? Because different materials have a different affinity or a different ability to hold on to electrons than other materials, okay? It's unique to each material. And so if one material has a stronger hold on electrons than the other, okay, electrons are pulled off of the material with the weaker hold, and they're transferred to the other material that has a stronger hold on electrons, okay? When this happens, both materials become charged due to either an excess or a deficit of electrons, okay? If a material has a strong attraction to electrons, it becomes negative. Okay, strong attraction to electrons will pull electrons off and become negative. If it's got a weak attraction to electrons, it becomes positive. Okay? So make sure you take a look at that and you kind of have that in your head set straight. If you've got a strong attraction to electrons, you're going to become negative. If you've got a weak attraction, you're going to become positive. Okay? So, here's an example of charging by friction. When you comb your hair, both the comb and your hair start off neutral. When your hair and the comb are rubbed together, electrons move from your hair to the comb, okay? Because the comb has a greater ability to attract electrons, okay? The comb becomes negative and the hair becomes positive. So look at this diagram, okay? If you look at the A part of the diagram, part that's further to the left, the A part of the diagram, what you'll notice is on the little girl, looks like a little girl, on the little girl's hair, if you counted the negative signs and the positive signs in the girl's hair, you'd find that there's the same amount of negatives to positives. Then, if you look at the comb in drawing A, you'll do the same thing. Same number of negatives, same number of positives, okay? So that's A, we got neutral. We got a neutral comb, we got neutral hair, okay? Now, what can happen here is when we rub the hair with the comb, this plastic comb rubs against the hair, okay? Your hair will lose electrons and the comb will gain electrons because the comb has a greater ability to attract electrons. So go into diagram B, just take a second and count how many negatives and positives are in the hair and how many negatives and positives are in the comb. What you're going to find is that there are less negatives in the hair than positives. And on the comb, there are more minus signs than plus signs. And that's because the hair has lost some of its electrons to the comb. So the hair has lost electrons, the comb has gained electrons. Okay? So we've lost electrons in the hair and we've gained electrons in the comb. And so what happens is the hair has a positive charge now. And the comb has got a negative charge now. Okay? So now the last thing I want to point out is compare the way the hair looks in both diagrams. In the first diagram, the hair is falling straight down. What do you notice is different in diagram B? Kind of looks like the ends of the hair are sticking out a little bit. And that's because the hair is now positively charged, the comb is now negatively charged. They're not in contact anymore, but as you pull the comb away, it's negative, the hair is positive. What happens to opposites? Well, they attract. So the hair is just a little bit attracted. The hair is just a little bit attracted to the comb. Okay? So we can see that static electricity, static charge can cause a little bit of an attraction. I just want to clue you in because we're going to talk a little bit about that in greater detail. But I just want to clue you into that little Easter egg that's in the picture there, which is really, really accurate. If you make the hair positive and the comb negative, well, they're going to be attracted to each other. So even when they're not touching, the hair is going to pull it closer. Okay? Only electrons can move. Protons do not move. Okay? So in this case, the proton stays solid. So you'll notice that in all the diagrams here, both A and B, the protons do not change. If you were to count them, the positive signs stay the same. In every diagram, in every object. The only thing that's changing are the negatives. Okay? So now we got to talk about the electrostatic series. Okay? The electrostatic series is a list of materials that's been arranged according to their ability to hold electrons. So materials that are closer to the top of the list have a weaker hold on electrons. They lose electrons very easily and become positively charged if they're rubbed with materials that are closer to the bottom of the list. Materials that are closer to the bottom have a stronger hold, and so they'll gain the electrons. They'll steal the electrons away. Okay? So this is the electrostatic series, and this is a diagram that I've taken out of your textbook. Okay? Now, you should have your textbook at home. If you don't have your textbook at home, we can't give you a physical copy, but hopefully you have looked around the content browser of the LMS page, and hopefully you found something that you're missing. Hopefully you found what you're looking for there. Okay, I can't say anything more than that, but hopefully there's something on there that can help you. Okay, because I can't give you a textbook because I don't have the copyright to the book, but maybe mistakes happen and sometimes you can find some Easter eggs. Okay, so look at this electrostatic series. We've got glass, human hair, nylon close to the top. We've got foam, polyester, grocery bags, that plastic grocery bags, and something called ebonite, which is a form of rubber on the bottom. And there's a series of substances in the middle. Okay, there's solids, they're materials in the middle. Okay, and here's what we got to do is we got to say, well, which one of these is going to be negative and which one of these is going to be positive? Okay, So if it is higher up, it will lose electrons. If it's lower down, it will gain electrons. Okay? So let's do an example. Let's say we took nylon and we rub nylon with polyester, which is something that we use in clothing. Okay? Which is going to gain electrons, which is going to lose electrons? Well, the thing that's going to gain electrons is the thing that's lower on the chart. So if we take nylon and we rub it with polyester, the polyester is going to gain the electrons. What charge will the polyester have? Well, it's gaining electrons, so it will be negative. What charge will the nylon have? Well, it will have lost electrons, and so its charge will be positive. Okay? And so that's really what that chart is for. And if I'm not mistaken, a lot of the homework questions are going to say, just like what I did, probably a little bit better than what I said, is that they're going to say, compare these two objects. When you rub them, what's going to happen? And hopefully I can find some YouTube videos that can demonstrate what happens when we do this. And I'll post those YouTube videos on the LMS, because what we have at Cathedrals, we actually have a box, and the box is full of it's got glass. It doesn't have any human hair in it. There's no human hair in that box. It's got nylon, it's got wool, it's got silk, it's got cotton, it's got lucite, it's got polyester, it's got ebonite. Okay, it has all of these objects. We usually pull that box out with the grade 9s. We say, hey, listen, let's rub these two objects together and see what happens. Okay, we can't do that right now because we're not in person and the box is at school and I'm not risking coronavirus to go get it. So we're going to have to see if we can find some stuff on YouTube that demonstrates that. But I think there should be some stuff on YouTube that does that. So I will post that online for you on the LMS so you can see it in addition to this video. So keep an eye out for that. Okay. Last thing we're going to talk about here, actually, maybe second last thing we're going to talk about here on this this section here. Oops. Insulators and conductors. So the materials listed in the electrostatic series are nonmetals, and they are considered insulators. That means they're materials in which electrons cannot move easily from one atom to another. So they can gain and lose electrons between materials, but the electrons can't flow through them. So what you'll notice is there are a lot of materials on there that are made of wood, of rubber, of plastic, because they don't allow electrons to flow. Remember what we said, static electricity was about the electrons. Well, we said the charge, but now we know charge is caused by electrons. It's about the electrons being able to stay static, stay in one place. And so that's why static electricity typically occurs. We're talking about insulators. Okay? Metals are considered conductors. So you notice on that list, there were no metals. Okay? Because metals don't hold a static charge. Metals allow electrons to flow. They allow electrons to move easily between atoms. And so those electrons can spread out easily through the material. And so the static charge is less easily observable in those metals. And there are some examples of metals. I'm sure that you know that those are metals at this point. Okay. Now there are some nonmetals in which electrons can move fairly well, and we call them semiconductors. Silicon is an example of a semiconductor. That is why we use silicon in a lot of computer chips, because electronics are basically, the basic principle is that electronics send a series of electrical signals through them. They're either sending a signal or they're not sending a signal. If it's sending an electric signal, that's a 1. If it's not sending an electric signal, that's a 0. And so for us to be able to do a lot of calculations on computers really quickly, for us to be able to do all the functions that we're doing on a computer or now a phone, or really any electronic device, we've got to be able to say, okay, we're sending an electric signal, we're sending an electric current, and then we're not. And we're sending it, and we're not. We're sending it, and then we're not. And we're sending it, now we're not. Okay? We've got to get those 1s and 0s out there. Now, this is not a computer class. You don't need to know about the 1s and 0s. They just mean electric signal or no electric signal. For us to be able to do that, we need materials for which we can sometimes pass electric current through and then stop that electric current. Silicon's a good material for that. That's why all the big software companies and computer companies, they're located in a place in California that has been nicknamed Silicon Valley. It's not because they mine silicon there. It's because they use silicon in a lot of the products that they build, okay? Because it is a semiconductor, okay? There was one more thing I wanted to say. What did I want to say? Oh, the last thing before we move further into the last slide is what's the obvious example of static electricity that you all know? You're wearing socks, you're walking on carpet, and you're rubbing your feet against the carpet, and then you walk up to someone, and what do? You touch them and you zap them, or you touch a doorknob or something metal and you zap yourself. That's because if your socks, maybe they're made of cotton, maybe your carpet's made of polyester, okay, there's a difference of charge, okay? I don't know what your socks are made of, I don't know what carpets are made of, doesn't matter, but there's a difference of charge, okay, when you rub them up together. Something is going to gain those electrons and something is going to lose those electrons. So when you're rubbing your socks against the carpet, there's an exchange of electrons. And when you walk up to somebody else or a metal doorknob and you put your finger near that person, what happens is your charge has to attempt to neutralize. And so you're going to shock yourself because electrons are going to be passed between either you and another person or you and a piece of metal that you've touched. Those electrons are going to try to balance themselves out because you've either gained or lost from walking on the carpet, and you're going to get a shock. Okay, tiny shock doesn't hurt that much. It's more annoying than anything, but you can now feel free since everybody's been home for well over a month now with their families. And I'm sure that no one's getting on anybody's nerves. Everybody's probably calm and stable. Now would be a good time to, particularly with your siblings, rub your feet against the carpet and then walk up to them and shock them. I'm sure that will not cause any problems for everybody who's been isolated for well over a month now. Sure, it'll be perfectly well appreciated as a funny joke now. Okay, but it's science. Okay, last slide here. Grounding. We want to remove static charge. Okay, the simplest way to remove the net static charge on an object is to put it in contact with the ground. Okay, a ground is an object that can supply a very large number of electrons to, or can remove a very large number of electrons from a charged object to neutralize it. What's the biggest object on planet Earth? Planet Earth is the biggest object on planet Earth. That's why when we have an excess of charge or we're missing charge, okay, we can connect ourselves to the planet Earth and we can neutralize ourselves, okay? It's called grounding yourself. And that's basically what happens when you rub your feet on the carpet. I don't have carpet here, it's tile, but when you rub your feet on the carpet and then you touch somebody else, what you're doing is you're trying to neutralize, okay? The charges want to be neutral. They don't want to have a charge, okay? Naturally, everything desires to be neutral. So Earth will remain neutral because it's so big that, you know, even if it's 1 or 2 electrons over or down, it's so massive that it's really able to absorb or supply electrons so that everything on Earth remains neutral, okay? Now, you can ground charge objects by touching them. Your body can receive or supply enough electrons to neutralize the charge. That is why if you're rubbing your feet, now not your body, but somebody else's body, when you're rubbing your feet on the carpet, you build up a charge in your socks, and then you go ahead and you touch somebody else, okay? And it works particularly well when it's dry, okay, which might not work too well now because we're hitting spring and it's kind of a little too moist out, but in the winter it's particularly effective, okay? When you rub your feet in, you build up charge, you touch somebody else's body, and you're using them as a ground, okay? So you're using them to neutralize your charge, okay? And it kind of hurts just a little bit, okay? So that is it for today's lesson. So what I'd like you to do now is to make sure you're doing the homework that I've assigned at the beginning of this presentation and on the student copy of the note. And then hopefully I've been able to find some YouTube videos that kind of show you this exchange of charge in motion to kind of help you visualize what's going on. And you watch those two. Those are going to be very, very helpful. So if I do post some additional YouTube videos here and you don't watch them, that's not a good idea. Make sure you do watch them because they're going to help you with this lesson. Okay? Until next time, please stay healthy, stay safe, take care of yourselves, take care of your family, and have a good day. Keep studying. Bye-bye.